Heat exchangers are conventionally used to transfer thermal energy between two or more fluids at different temperatures.
A shell and tube exchanger consists of several tubes mounted inside a cylindrical shell in which two fluids can exchange heat. One fluid flows over the outside of the tubes while the second one flows through the tubes. The fluids can be single or two-phase and can flow in a parallel or a cross-counter flow arrangement.
To establish the mesh of the heat exchanger, several models were considered in order to properly simulate the fluids inside it.
The polyhedral mesh, as its name implies, generates polyhedral cells. This kind of mesh was chosen because their cells are superior to tetrahedral ones due to their large amounts of phases. Polyhedral cells have lower skewness, which improves the accuracy in calculations and creates a more homogeneous mesh.
Moreover, polyhedral mesh compared to tetrahedral mesh requires 5 times less cells to reach the same level of accuracy, which results in fewer time of simulation.
To capture the hydrodynamic boundary layer in the correct way, we use the Prim's layer measure, where prismatic cell layers are located near the different wall boundaries.
The embedded thin measure option was selected and thickness threshold option was enabled, which allows monitoring of the modeling of the hot fluid tubes. Before running, it was necessary to define the physical model that described the behavior of fluids in the heat exchanger.
A total number of 684,544 cells was obtained. This one indicates acceptable meshing since an expected value for cell quality would have been found around 0.67.
The worldwide plus presents values of the tubes that are mostly kept below 1, although in some points they tend to be very scarce. Two large values are found, such as 12 or even 50. Three simulations were carried out in parallel and three in conjugate, with temperatures of 55, 60, and 65 degrees Celsius, and volumetric flow of cold and hot fluids set at 3 and 3.5 liters per minute, respectively.
Regarding the results, the values calculated by STAR CCM Plus were obtained, as well as the values calculated by the CACAC method in MANDA. First, it is recognized that the energy balance must be studied in both methods, whether the fluid is countercurrent or in parallel. Likewise, the LMTD value comes from the following expression. That finds the average value of the hot and cold temperature in a differential zone of the heat exchanger. We calculate it using the bulk temperature for each fluid. For the CACAC method, the area of the fluid's inlets and outlets and the speed of the hot and cold fluids were determined. First, for the calculation of the shell, the hydraulic diameter for the side part considering relevant measurements was calculated. Also, the bundle cross flow area was calculated with the values presented in the following equation. And the mass flow calculation was taken as the product of the bundle cross flow area and the volumetric flow. These values were useful to calculate the Reynolds number. Later on, the Prandtl number and the nozzle correlation were calculated in order to calculate the heat transfer coefficient for the cold fluid. On the other hand, the calculations for the tubes were made to obtain the heat transfer coefficient of the hot fluid. The calculations of the Reynolds number and the nozzle correlation were calculated differently on this part of the heat exchanger considering the flow regime. For values of Reynolds below 3200, it is considered a laminar flow regime, in which the nozzle correlation is calculated using the following equation. For values of Reynolds above 4000, it is considered a turbulent flow regime, in which the nozzle correlation is calculated. For values of Reynolds between 3200 and 4000, it is considered a transitional flow regime, in which the nozzle correlation is calculated by an average between both laminar and turbulent values of nozzle correlation. Finally, the heat transfer coefficient for the hot fluid was calculated using the following equation. The energy balance is carried out and it is observed that, although it does not completely converge, the difference is not too noticeable, and that it may have to do with the fact that we're assuming that we will not have losses anywhere and that no heat is being consumed transferring through the shell. The use of the value F was considered so that it corrects the balance. However, It was not found because the value of F must be less than 1 and no reason less than 1 could close our balance. On the other hand, CFD heat calculation give results that converge much more with each other and allow us to find the values of F, showing that this method tends to be much more precise as it would be expected to happen.
A comparison between heat flow and global transfer coefficients can be made, showing that for every case, values tended to be similar, yet noticeable differences were especially noted in the global heat transfer coefficient U, which depicts the most prominent error percentages. While this aspect indicates that large differences in hot and cold heat transfer coefficients play very significant roles in some calculation results, CACAC method still can present very low errors in the heat flow obtained for each case. To better understand our results, a graph that compares CACAC and CFD results for heat flows obtained at multiple values of LMTD was made. The graph for parallel flow indicates that both CFD and CACAC results maintain linear behaviors, while the graph for countercurrent flow goes to depict that CFD maintains a polynomial behavior, which could indicate that CACAC method might be more accurately applied in the study of parallel configurations. Moreover, a comparison of the heat transfer configuration given a certain method of calculation presents that larger amounts of heat are transferred in countercurrent configurations, regardless what the method of calculation is. And once again, it is noted that countercurrent flow behaviors are less easily predicted with CACAC's method. The suggestion is made that for a future study of systems such as the heat exchanger, the energy lost by the shell is considered, and that more accurate Reynolds calculations may be used. Also, study of a more complex or just bigger in size heat exchanger might come in handy to obtain more accurate and realistic results. Finally, although it is recognized that the CFD gives better results, the CACAC method should not be ruled out, but on the contrary, it could serve on occasions when there is no access to simulation program and still give results that are within what we consider acceptable.